Distillation towers are designed in a variety of ways to meet the demands of particular applications. A distillation tower, or column, can be categorized by the number of products that leave the tower. Two common types of towers that are identified this way are binary towers and multi-draw towers. A binary tower separates a feed into two products. For this reason, you may also hear a binary tower referred to as a two-product tower. Some binary towers separate one light component from a range of heavier components, but they are still considered to be binary towers because only two products leave the tower. Multi-draw towers separate a feed into more than two products. A product that leaves a multi-draw tower is referred to as a draw or a stream. Multi-draw towers are also referred to as side-draw towers because some of the products or draws are taken from the side of the tower. For example, one type of multi-draw tower has three draws, one at the top, one at the bottom, and one near the middle. Because a draw or cut is taken out of the middle of this tower, this type of tower is sometimes referred to as a heart-cut tower. Multi-draw towers can also have more than three draws to separate several products from a feed. This one is an atmospheric tower in a crude oil distillation unit. An atmospheric tower is so named because distillation takes place in it at or near atmospheric pressure. Now that we've established the difference between binary towers and multi-draw towers, let's focus on the operation of a typical multi-draw or side-draw tower. The multi-draw tower illustrated here is used to separate a mixture into four products. Each product may be made up of one or more substances. The tower has four draw-off lines located at different levels. The draw-off lines provide a means for removing the products of the distillation. We'll number the products 1 through 4 to identify them. The illustration also shows two devices called strippers or side stream strippers: a condenser, a receiver, and a reboiler. Cooling water reaches the condenser through this line. Steam reaches the strippers through these two lines. And steam reaches the reboiler through this line. After the feed mixture is preheated and introduced into the tower, the heaviest components move down the tower, while the lighter components vaporize and move up the tower. The temperature at each draw-off point is important for the proper separation of the products. For example, the temperature is the highest at the bottom of the tower, where product 1 is drawn off. Here, the temperature is hot enough to vaporize the components that become products 2, 3, and 4. But it is controlled to minimize the amount of product 1 that vaporizes. If we move up the tower to the area where product 2 is drawn off, the temperature is lower than it is at the bottom of the tower. While there may be some overlap of products in this area, the concentration of product 2 is highest in the liquid that is drawn off at this point. If conditions in the tower are controlled properly, the concentration of each product is highest at its respective draw-off point. Let's take a moment to see how draw-off is collected. The liquid in each tray in the tower collects to the height of a weir, which is a dam-like barrier that holds the liquid on the tray at a specific level. If the tray is at a draw-off point, a portion of the liquid is drawn off through a draw-off line. The liquid overflow from each tray is allowed to flow to lower trays through passages called downcomers. This liquid is called internal reflux. This arrangement helps to ensure that any heavier components of the liquid have a chance to travel down to their proper draw-off points. The liquid that is drawn off by each side draw line goes to a side draw stripper. Each stripper is basically a small distillation tower. Its function is to remove or strip off any lighter products from the liquid. Liquid from the tower enters at the side of the stripper. In the stripper, the liquid is heated by steam, which causes any lighter products in the liquid to vaporize. The vapors that are produced are reintroduced into the tower above the tray from which the original liquid was drawn off. The liquid that is left over in the bottom of the stripper is drawn off as a product. The products or cuts obtained from the distillation process are sometimes called fractions. For this reason, distillation towers are sometimes called fractionating towers or fractionators. The physical dimensions of distillation towers may be different. In general, they are most affected by three main factors: the relative volatility of the feed components, the feed rate, and vapor loading. Relative volatility is the relationship between the boiling points of the feed components. Feed components that have a low relative volatility are difficult to separate because their boiling points are close to each other. In order to effectively separate the components of a feed with a low relative volatility, a tower requires a large number of trays, and in order to accommodate those trays, the tower must be fairly tall. The second factor that affects the physical dimensions of a tower is feed rate. Basically, higher feed rates require towers that are larger in diameter. The third factor that affects the dimensions of a tower is vapor loading. Vapor loading refers to the total volume of vapors generated by the reboiler, and the vapors produced as a feed enters the tower's flash zone. The flash zone is the section of the tower where the feed enters and some of it vaporizes. Higher rates of vapor loading generally require a larger diameter tower. Lower rates of vapor loading can be handled in a tower with a smaller diameter. Some distillation towers operate at a low pressure. In these towers, a tremendous volume of vapors may be produced, so the diameter of the tower must be large to handle the vapor volume. Since a lower volume of vapors will be produced in a distillation tower that operates at a high pressure, the diameter of the tower can be relatively small. Another way a tower may vary is in its function. For example, the function of one type of tower is to separate or split components in one boiling range from components in another boiling range. This type of tower can be called a binary tower, a two-product tower, or a splitter tower. For some product specifications, it's necessary to separate light components to control the product's initial boiling point. To meet these specifications, some processes use distillation towers called stabilizers. Another type of tower is called a stripper tower because it strips lighter components out of the products. However, unlike most other distillation systems, a typical stripper tower system does not condense the overhead product into a liquid. Instead, the overhead product remains as a vapor and is sent for further processing. Some towers are named according to the chemical product that is being separated. For example, a tower that separates propane and lighter components from a feed can be called a depropanizer. The overhead product from a depropanizer contains mostly propane and some lighter components. Components that are heavier than propane end up in the bottoms product. Many distillation towers operate at or near atmospheric pressure. There are some distillation towers, however, that are designed to operate at pressures lower than atmospheric. These types of towers are called vacuum towers. Vacuum tower operation is based on the fact that pressure affects the boiling temperature of a liquid. For example, water boils at 212 degrees Fahrenheit at standard atmospheric pressure, which is 14.7 pounds per square inch, or psi, at sea level. If pressure is decreased to 6 psi, water boils at 170 degrees Fahrenheit. When the pressure inside a tower is reduced, liquids are vaporized at lower temperatures. This process is referred to as vacuum distillation. Now, keep in mind that a vacuum tower does not operate under a perfect vacuum. Vacuum distillation simply means that the pressure in the tower is lower than atmospheric pressure. Vacuum distillation is used for several reasons. First, one or more components in some liquid mixtures may decompose or be damaged at high temperatures. If such a mixture is distilled at high temperatures, an unwanted product may result. A second reason for using vacuum distillation is that running a tower at high temperatures requires more energy or fuel. Operating a tower at lower pressures allows the distillation process to be accomplished at lower temperatures, which requires less energy. A third reason for using vacuum distillation is that a tower that's designed to operate under vacuum, and therefore at a lower temperature, can be constructed of materials that do not have to be specially made for high temperature operation. Structurally, there are two basic differences between a vacuum tower and a tower that operates at atmospheric pressure. We can use this illustration of a vacuum tower system to see what the differences are. For example, a vacuum tower is usually larger in diameter than an atmospheric tower, and the trays are farther apart. These differences are necessary because a vacuum tower generally produces a larger volume of vapors than an atmospheric tower. Another difference is that a vacuum tower has an additional system that creates and maintains a partial vacuum in the tower. The partial vacuum is maintained by either steam jet ejectors or a vacuum pump. These components draw gases out of the tower through the condenser. Azeotropic distillation is a process that is sometimes used with mixtures whose components are difficult to separate. Essentially, an azeotropic mixture behaves as if it were a pure material. The vapor produced by boiling an azeotropic mixture contains the same percentages of components as the original mixture. Even if more heat is applied and all of the mixture vaporizes, the vapor composition remains the same. One way to separate an azeotropic mixture is to use a solvent. The solvent is a substance that, when combined with the azeotropic mixture, allows the separation of components to take place. Another way to separate an azeotropic mixture is to use two distillation towers in a special arrangement. In this topic, we looked at different types of towers commonly used in distillation systems. We also looked at some factors that can affect the physical dimensions of a distillation tower. In addition, we looked at a vacuum distillation and azeotropic distillation. Now try some practice questions that relate to this material. Multi-draw towers separate a feed into more than two products. A product that leaves a multi-draw tower is referred to as a draw or a stream. Multi-draw towers are also referred to as side draw towers because some of the products or draws are taken from the side of the tower. For example, one type of multi-draw tower has three draws, one at the top, one at the bottom, and one near the middle. Because a draw or cut is taken out of the middle of this tower, this type of tower is sometimes referred to as a heart-cut tower. Multi-draw towers can also have more than three draws to separate several products from a feed. The physical dimensions of distillation towers may be different. In general, they are most affected by three main factors: the relative volatility of the feed components, the feed rate, and vapor loading. When the pressure inside a tower is reduced, liquids are vaporized at lower temperatures. This process is referred to as vacuum distillation. Now, keep in mind that a vacuum tower does not operate under a perfect vacuum. Vacuum distillation simply means that the pressure in the tower is lower than atmospheric pressure. One way to separate an azeotropic mixture is to use a solvent. The solvent is a substance that, when combined with the azeotropic mixture, allows the separation of components to take place. A reboiler is basically a heat exchanger that heats bottoms liquid from a distillation tower and vaporizes the lighter components in it. Often, a reboiler provides most of the heat that's needed for distillation to occur in a tower. Two ways that reboilers can be categorized are by how fluids circulate between the tower and the reboiler, and by the location of the reboiler in relation to the tower. Fluid circulation between the tower and the reboiler can be forced circulation or natural circulation, and a reboiler can be an external reboiler or an internal reboiler. Let's begin with a look at forced circulation systems. In a forced circulation system, a pump moves fluid between the tower and the reboiler. Furnaces like this one are sometimes used as reboilers in forced circulation systems. This type of furnace is known as a fired reboiler. We can use an illustration to see how this system operates. It includes the bottom of a distillation tower, a fired reboiler, and a pump. During operation, part of the liquid from the bottom of the tower is pumped to the reboiler, where it is heated by the burning of fuel in the furnace and its lighter components vaporize. A mixture of the vapors and any remaining liquid is returned to the tower, where it provides heat for the distillation process. The pump also moves part of the liquid from the bottom of the tower to storage or to other processing equipment. This liquid is the tower's bottoms product. A shell and tube heat exchanger can also be used as a reboiler in a forced circulation system. Steam is often used as the heating medium in this type of reboiler. As the steam gives up its heat to the liquid in the reboiler, the steam turns to condensate, which flows out of the reboiler. The vapor-liquid mixture that is produced in the reboiler is returned to the tower. Shell and tube reboilers use various fluids as heating media. For example, instead of steam, some systems use a hot fluid from another process, such as the hot product from a process reactor. As we've seen, a forced circulation reboiler system requires a pump to move liquid. Reboiler systems that do not use pumps to move liquid from the tower are called natural circulation systems. In these systems, liquid circulates naturally as a result of the difference in density between the liquid in the tower and the liquid in the reboiler. One type of reboiler that's used in natural circulation systems is a thermosiphon. A thermosiphon is basically a shell and tube heat exchanger. We can use a simplified illustration of a thermosiphon and the bottom of a distillation tower to see how liquid is circulated without a pump. Some of the liquid in the bottom of the tower is taken off as bottoms product. The rest of the liquid flows by gravity into the bottom of the thermosiphon. As steam is fed into the thermosiphon, part of the liquid in the thermosiphon vaporizes. The mixture of vapors and hot liquid is less dense than the liquid at the bottom of the thermosiphon. The lighter, less dense mixture of vapors and hot liquid rises in the thermosiphon and is returned to the tower. When the mixture of hot liquid and vapors leaves the thermosiphon, cooler, denser liquid from the tower flows into the thermosiphon, establishing flow through the reboiler system. Another type of reboiler that's commonly used in a natural circulation system is a kettle reboiler. A kettle reboiler looks a lot like a shell and tube reboiler. The major difference is a dome-shaped section on top of the reboiler. A hot fluid, such as steam, is fed into the tubes of the kettle reboiler. Part of the liquid from the bottom of the distillation tower flows into the shell. A weir ensures that the tubes in the reboiler are kept covered with liquid. The vapors collect in the domed space in the shell and are then returned to the tower. Any liquid that is not vaporized is bottoms product that is sent on for further processing or storage. Another way that reboilers can be identified is by their location in relation to a distillation tower. A reboiler that is located outside of a tower is an external reboiler. All of the reboilers we've seen up to this point are external reboilers. A reboiler that is mounted directly into the bottom of a distillation tower is an internal reboiler. This particular internal reboiler is often called a heating element or stab-in reboiler. In general, internal and external reboilers work in much the same way. Steam or another hot fluid is used as the heating medium, and the vapors or vapor-liquid mixture that is produced is used in the tower to provide heat for distillation. An important part of a distillation process is the overhead system, and one important piece of equipment in the overhead system is a condenser. A condenser in an overhead system is often referred to as an overhead condenser. The condenser is used to convert the vapors produced during distillation into a liquid. It does this by lowering the temperature of the vapors. One way that a condenser in an overhead system can be classified is by the type of cooling medium it uses to cool vapors from distillation towers. Among the media most commonly used are air, water, and refrigerant. One type of condenser that uses air to cool vapors is a fin fan or forced air condenser. During operation, motor-driven fans blow air around tubes in the condenser. Vapors from the tower flow through the tubes. The air absorbs heat from the vapors, causing them to condense into a liquid. The liquid or distillate then collects in a receiver. Water can also be used as a cooling medium. The water in a water-cooled condenser has the same basic function as the air in a fin fan condenser. This is a simplified illustration of a condenser that uses cooling water to convert vapors into liquid. The condenser consists of a shell, tubes, tube sheets which support the tubes, a vapor inlet, a cooling water inlet and water box, a cooling water outlet and water box, and a distillate outlet. The illustration also shows a receiver. During normal operation, cooling water enters the cooling water inlet, fills the water box, and flows through the tubes. The cooling water then passes through the outlet water box and leaves through the cooling water outlet. At the same time, the product vapors enter the condenser through this vapor inlet and flow around the tubes. When the vapors come into contact with the surfaces of the tubes, heat is transferred from the vapors to the cooling water in the tubes. As a result, the cooling water is heated and the vapors are cooled. This causes the vapors to condense on the tube surfaces. The distillate drips off the tubes and flows through the distillate outlet to the receiver where it collects. Refrigerant can also be used as a cooling medium. Like air and water, refrigerant absorbs heat from the hot vapors. A condenser can also be classified by the role it plays in a distillation system. For example, a condenser that condenses all of the vapors from a distillation tower may be called a total condenser. A condenser that condenses most but not all of the vapors from a tower can be called a partial condenser. In this topic, we looked at some of the reboilers and condensers used in distillation systems. Now try some practice questions that relate to this material. In a forced circulation system, a pump moves fluid between the tower and the reboiler. One way that a condenser in an overhead system can be classified is by the type of cooling medium it uses to cool vapors from distillation towers. Among the media most commonly used are air, water, and refrigerant.